Alright, so today we're going to move on and talk about universal gravitation. So we often talk about universal gravitation at the same time we're talking about circular motion, because the motion of, say, the moon around the earth or the earth around the sun can be approximated as circular motion, so they kind of pull together. And universal gravitation is actually a law. It was a law created by Isaac Newton. And he basically had some questions that he pondered. And so you've probably heard the legend of him sitting under the apple tree, watches the apple fall and says, hey, why did the apple fall? Why isn't everything falling right now? Does everything want to fall? So he figured that there was some force pulling the apple down towards the earth. And this is what the idea of kind of defining gravity. Now, long before Newton, Galileo had already determined the acceleration due to gravity. So we knew that objects accelerate due to gravity at the same rate. So there must be something unifying the fall of all objects. But what about what was going on in the solar system? What about the moon? If the apple wants to fall down to the earth, why doesn't the moon fall down to the earth? Why does the moon keep moving in a circle? So what Newton did was a thought experiment. He's figured out, okay, what happens if I could put a cannon really high up on like a very big mountain, or build a very, very big tower. And what he did is then he thought about launching projectiles horizontally, so tangentially to the radius of the earth, so he could give it a tangential velocity. And you've done this probably before. You've probably been forced to throw a ball, or wanted to throw a ball. And if you don't throw the ball very fast, what happens is it collides with the earth. If you throw it a little bit faster, it's going to be able to travel further before it collides with the earth. Now, when we think of throwing a ball, we usually imagine that the earth is flat, so the ball is making just paths and going different horizontal distances, but really the earth is curved, and if you could get it fast enough, you would start getting it to move past this curve. And if you could get it even faster, at some point in time, you could get it fast enough to make an elliptical orbit around the earth. And if you've learned about conic sections in pre-cal, what you probably know is that an ellipse is just one of the different conic sections, and that a circle is a special case of ellipse, so that if I could have one particular speed is going to be able to give me that perfect circular orbit. And then if I shoot it any faster past that particular speed, then I can get bigger elliptical orbits. And eventually, if I could shoot it even faster, we can get an open orbit that doesn't close. And actually, this open orbit that doesn't close is actually a parabola. So it's a parabolic orbit. It's called an open orbit because it doesn't close back on in itself. And if you go even faster, you can actually get a hyperbolic orbit, so we can get all the full conic sections. So we figured out that basically, if you can get this apple, if you throw this apple fast enough, it's still always going to fall to the earth. But if I could throw it fast enough from a high enough height, then I could actually get that apple into orbit. So the same force that is governing the fall of the apple is governing the motion of the moon. And that's why it's a law of universal gravitation, because it universally explains everything. Unless you get down at a subatomic, super subatomic level, or you end up going at speeds that are faster than light. So there are limitations on this universal gravitation. Now, he did some experimentation, and these were the experimental observations that he came up with. So after doing a bunch of tests, he figured out that the force of gravity acts between all objects. He figured out that if mass increases, force of gravity increases. Shorten it there. He figured out that if distance increases, then your force of gravity decreases. So you had an inverse relationship between distance and gravity, whereas you have a direct relationship here between mass and gravity. And he figured out that basically if you could treat all objects as perfect spheres, perfect uniform spheres of basically no volume, no size is really what helps, then if this was object 1 and this is object 2, and object 1 has a mass m1 and object 2 has some mass m2, and you knew the distance essentially between their centers, if they were perfect spheres, and he uses the distance r for that. We use r for position in a lot of circular type cases. That with knowing that information, then you could find proportionately how the force of gravity would change. And basically what he said is all objects are exerting a gravitational force. So object 2 is pulling object 1 towards it. So there is a force of gravity of object 2 on object 1. And it acts along this radial line between them. And there has to be a force of gravity of object 1 acting on object 2. So object 1 is also pulling object 2 to it. It doesn't matter if object 1 is massive and object 2 is tiny, both of them are exerting forces. And Newton's third law tells us that these forces of gravity must be equal and opposite. So it doesn't matter what the difference in masses is. Right now, you are pulling the Earth to you just as much with an equal force as the Earth is pulling on you. Now, mathematically, what he figured out is that the force of gravity was always proportional to the product of the masses over the radius squared between them. This is what Newton was able to figure out. And he basically figured out that there was a proportional relationship, and he knew that the force of gravity for 2 on 1 had to equal the force of gravity for 1 on 2. That was what Newton was able to figure out. Now, this is just a proportionality statement. We want an equation. We want to actually be able to do calculations with this, not just analyze proportions. So there is a constant that if you were to set up a linearization type activity, if you could do that, that you could actually prove what the constant is that makes this an equality. And that force of gravity is equal to G m1 m2 over r squared is Newton's law of universal gravitation, where G is essentially a proportionality constant. So with this equation, notice that the force of gravity is proportional to m1 and m2. So what that means is if I was to double m1, I would double my force of gravity. If I was to double m2, I would double my force of gravity. If I were to double both, I would quadruple my force of gravity. And the force of gravity is proportional to 1 over r squared. So if I were to double the separation distance between them, I would get 1/4 of the force of gravity. So this is what we call an inverse square law. We will see other inverse square laws as we go through the year. And what the inverse square law tells us is basically that this force of gravity is going to decrease rapidly with radius. So for example, if I was to graph this function, so if I was to graph the force of gravity with radius, what I would find is I would find something that looks kind of like that. And so if I was very, very, very close to the surface of the Earth, I can assume gravity was constant. But if I get really far from the surface of the Earth, like even as far as the moon or as far as Pluto, then you're going to get really small decreases. So we have the Earth has a pretty big impact on the moon. Okay, we're holding the moon in an orbit, actually holding it in place. So the same side of the moon is actually always facing the Earth, which is kind of cool. But Pluto has very little effect on it due to the Earth. And basically what this says is the only way to actually escape the force of gravity of an object is to get infinitely far away. So you are an object that is exerting a force of gravity on all of the objects around you. And the world really does all depend on you, because you have to get infinitely far away from you in order for you not to have a gravitational force on it. But it doesn't take much distance to get, so that force is negligible, so sorry. Now, if we were to look at the masses, the force of gravity difference with mass, so assuming that radius actually stays changed, that is a linear relationship. So if we were to, say, plot M1 or M2, you'd get a linear relationship there with that. And basically, if you were to be able to plot a graph where this is, of course, this assumes mass is constant, this assumes radius is constant. If I were to plot my force of gravity and M1, M2 over r squared, if I could know all of that information, then that would be a linear relationship, and the slope of this graph would equal g. And so what is that g and what does it mean? It is literally a proportionality constant. And it's called, I think it's called a gravitation constant. So it's the universal gravitation constant. It was not discovered by Newton. And it is equal to 6.67 times 10 to the negative, oh, that 10 didn't come out very well, 10 to the negative 11th Newton meters squared per kilogram squared. So it's a proportionality constant that actually makes this true. And so this value is true kind of for our universe. So if you were to use this for any object, it could be you in your chair, it could be you and the Earth, it could be the Earth and Pluto, and you would be able to accurately calculate the force of gravity if you were able to know the mass of all of those objects and the separation distance. And that separation distance, remember, is from their centers. So when we said that the force of gravity was equal to m times g, that force of gravity is the same as this force of gravity here. So let's say I was talking about the Earth and someone standing on the Earth. Okay, and let's call the Earth m1, let's call the person m2. So before, what we would have said is, okay, my force of gravity of the Earth on me, okay, so the Earth on me would have been m1 on m2 is equal to m, and that would be my mass times g, as long as I stayed near the surface of the Earth. And then if I actually used this equation, and I knew m1 and I knew m2, and I knew the radius of the Earth, then if I set my radius r equal to the radius of the Earth, then this force of universal gravitation would be g m1 m2 over r squared. That force of gravity and this force of gravity have to be the exact same thing. So this is the force of gravity of the mass 1 on mass 2. It's also the force of gravity of mass 2 on mass 1. So that works in either case. But I can just set that equal to m2 times g. And with m2 times g, and I look at this statement right here, these two are equivalent statements for gravitation, for the gravitational force on me. Now you notice that my mass, standing on the surface of the Earth, actually cancels out of this equation. And you end up with g times m1 over r squared equaling g. So this is the acceleration due to gravity. Now, if I'm close to the surface of the Earth, this m1 would be the mass of the Earth. This r2, essentially, because I'm very small compared to the radius of the Earth, would be just the radius of the Earth squared, and that would be g. So if you plug in the mass of the Earth, and you plug in the radius of the Earth, you end up getting 9.8 as your answer. The mass, the accepted value for the mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth, and this is the average equatorial radius of the Earth, is equal to 6.38 times 10 to the 6th meters. And we already have our value for g, so you can try it, plug it in, and you should get a value that is equal to 9.8 meters per second squared. All right, so the last topic for today is going to be talking a little bit more about this little g value, which we've always referred to as the acceleration due to gravity, but more commonly, more generally, it's referred as the gravitational field strength. And instead of having units of meters per second squared, we normally represent it as newtons per kilogram. We're talking about this universal gravitation idea, because the gravitational field strength is the ratio of the gravitational force to the mass of, you know, the object in the orbit, or that is experiencing the gravitational field. So what this does is it basically eliminates the second object from consideration of field strength. So I can analyze the strength of the gravitational force of, say, the Earth at any location in the universe without having to have a test mass putting in there feeling the force of the Earth. So this allows us to study like the gravitational field strength of the Earth in different ways. And there is a lot of research that goes in. There's a lot of, the GRACE satellites were sent out to measure the gravitational field strength at different locations in the Earth. So we can look for gravitation anomalies and things. Where is there a stronger gravitational field than the areas around it? We can use it for topographic mapping and all sorts of different things. So this is a very, very powerful tool. So if, say, like a comet comes near Earth or anywhere in the solar system, and we don't know what the mass of that comet is, I can still figure out how much gravitational field strength it has, and essentially what its acceleration, rate of acceleration would be at any position, just by knowing the mass of the Earth and how far away that object is from the Earth. So for example, the ISS is in orbit around the Earth. It orbits at an average of like around 400 kilometers or so. And it completes its orbits. And a lot of times you see images of the astronauts in the ISS looking weightless, like they are floating. So you'd think, well, there's no gravity then. If they're floating, they're not being pulled down, then there can't be any gravity. Well, the problem is that there is gravity. And actually, if we plug in these values into this equation where we let r equal re plus h, then what you would find is that if you calculate g, that gravitational field strength is something around 8.7 meters per second squared. So that's actually not that much smaller than the acceleration due to gravity on the surface of the Earth. It is smaller, but not enough for there to be no gravity. So why does it look like the astronauts are weightless? Remember that our feeling of weight comes from our weightlessness. I don't think that's right, that's okay. Comes from our experience of normal force. So weightlessness means that our normal force is 0. It doesn't mean our gravitational force is 0. So because those astronauts are falling towards Earth at the exact same rate as the ISS itself, they can't exert a normal force on the ISS. The normal force can't, the ISS can't exert normal force back on them. Now, because they're moving with a tangential velocity, basically as they fall around the orbit, as they move, they're constantly trying to move in a straight line, but they're getting pulled back down. So that's why they don't fall towards the Earth, because they're moving tangent to it and then kind of falling as you go. But they are constantly falling, and they're not experiencing no weight. Basically, they're experiencing no normal force. That's why they appear to be falling. All right, so I hope that gives you a good feel for universal gravitation.